Our last improvement to our disjoint sets data structure is going to be something known as path compression. Now this is a bit of a preview of what one might see in CS 170, the theory course here at Berkeley. And that said, I still want to walk you through it because the idea is beautiful, though the analysis will be well beyond our capabilities. All right. So to summarize what we've achieved so far, we started with a list of sets, disjoint sets, data structure, and it had relatively poor performance. It was linear for connect and is connected in the worst case. By a sequence of clever improvements, we were able to get to login performance for these operations, which is far, far better. So now if we think about not just a single operation, but im operations, so we're imagining that we have a service running on the internet, and we have in objects that our service is keeping track of. Let's say that im is the total number of operations that are being made to our disjoint sets object. Let's say, im represents people trying to friend people on our social network or send messages or whatever. Im is the things that people are doing, the connect and is connected operations. So for our naive implementation, that really bad one, doing im operations on a disjoint sets object would be big O of im in, right? So if each operation takes big O of n time, then doing im of them will be im times n. Now for our best implementation, this one that is weighted quick union, what happens is that the overall runtime is big O of n, just to construct the object. And then for each of our operations, they each take log n time, and there's m of them, so the overall runtime is m log n. So if we imagine that n is a billion, and im is also a billion, then the difference between these two, if you just plug in the numbers, would be something like 30 years versus 6 seconds. So that's really great. Instead of having to spend 30 years of computation time to handle all these queries that people are making, we only need 6 seconds. And that, as I alluded to in an earlier lecture, is really where the magic happens, when you get better asymptotic performance. We unlock solution to problems that could not otherwise be solved. If we had to wait 30 years for our answers, let's say in some scientific simulation, that's just too long. But 6 seconds is great. And then we could try out different parameters and do whatever else in our simulation and get cool results. So what we've got so far, it is good enough for all practical uses that we might want. But just as a point of intellectual curiosity, we could ask ourselves, is there a way to do better than log n? And it turns out you actually can. So below, I'm showing you the worst case if we use weighted quick union. We saw this before. Okay? So here, let's imagine someone calls isConnected 15 and 10. So usually, that would involve climbing the tree. 15, who's your boss? 11, 11, who's your boss? 5, 5, who's your parent? 1, 1, who's your parent? 0, who's your parent? Nobody. Okay, so we climbed the tree and spent some computation time. Same deal with 10, 3, and 0. What we could do is, since we already now, at this moment, found who is the root of 15, 11, 5, and 1, we could actually just set all of those values equal to 0. In other words, I'll set the parent of 15 to 0. Now, very important point. This changes nothing about which set each item belongs to. 15, 11, 5, and 1 are all still just part of the set owned by 0. In fact, if you think about it, all of these items are all in the tree where 0 is the root. And what we're doing here is now we're kind of, if you know the idea of memoization or caching, we're going to set aside information that 15, 11, 5, 1, 10, and 3 are all part of the set where 0 is the root. So we just set all their value to 0. Okay? Now the additional cost to do this is insignificant. It's the same order of growth, but now future queries will be faster. If we say are 15 and 10 connected, we know immediately. We just climb up one level for both, and we're done. So to see if this really makes sense to you, let's imagine we call isConnected for 14 and 3. What will the overall tree look like? Try drawing it. Okay. So the idea here is we have to walk up the tree. We find 14, 8, 2 on one side and 13, 6, 1 on the other. And so what we do now is, as part of the isConnected process, we will tie them all directly to the root. And now redrawing it so that it looks nice, we end up with this shorter tree. So this approach, we end up with a tree which is much simpler. And you can imagine if you keep calling isConnected over and over, you're going to end up getting this very flat tree where all the items will be direct descendants of the root. Okay. Now this approach, it results in operations that are very, very close to amortized constant time. Now here, amortized is a word that is used to mean average. So that on average, I mean, the first few operations are going to be expensive because, the tree might be up to log height. I mean, that's not that expensive, but they'll be log expensive. But over time, they'll get cheaper and cheaper. So there's actually an analysis you can do that says that doing m operations on n nodes with this data structure will be, instead of n plus m log n, it'll be m log star of n. That's an upper bound you can make for the runtime. So what is log star? Well, it's a function known as the iterated logarithm, where you can see it here, basically, that if n is 16, the log star of n is 3. In order to get up to log star of n, we actually need to get up to an n which is 2 to the power of the previous item. So here, we have to get up to 65,536 in order to reach a log star value of 4. To get up to 5, n would have to be 2 to the 65,536. To get up to 6, it would have to be 2 to the 2 to the 65,536. That is a huge number. And in fact, we can say that for any realistic input, for anything that anybody might want to do for any purpose in our universe, log star is less than 5. So technically, log star, it's not a constant function, but it is a function for which any computer that will ever be built in the entire conceivable history of mankind, it will be less than 5. Now, it turns out that this is actually a somewhat pessimistic analysis. You'll see it if you take CS170, but you can actually prove an even tighter bound. So there's a somewhat straightforward analysis that says it's never going to be worse than n plus m log star n. But with a little more cleverness, you can actually show that the bound is tighter. It is not log star n, but is bounded above by the inverse Ackermann function of n. Now this is an even more slowly growing function where to get up to 5, we have to do, I'm not even really going to go into it to explain exactly what it is, but I have here in notation that we would need 2 to the 2 to the 2 to the 2, up to 2, and that would be 65,536 levels deep in order to get to 5. So, it's even a little slower. But this is CS theory, right? This is not something where you're working at a company or on a startup or on your own personal project and you think, can I somehow get from log to inverse Ackermann? It won't affect you too much. And certainly the difference between iterated logarithm and inverse Ackermann is a purely intellectual exercise. Now it's kind of a cool, if you want to know, like if you want to see the actual analysis that led to this and you're curious how it works, there is a paper called The Efficiency of a Good but Not Linear Set Union Algorithm, and that was written by Bob Tarjan while at UC Berkeley back in 1975. Bob actually, by the way, when I was at Princeton, one semester I had him as one of my TAs because we had a thing where faculty would rotate through as TAs for classes, and that was pretty fun. I liked having Bob as a TA. So, to summarize our iterative design process we had today. We are now done. The end result of this design process is the way that disjoint sets are implemented in real-world libraries. We use quick union and path compression. Often weighted, but you actually don't need weighted for good performance as long as you have path compression. Now, the ideas that made our implementation efficient, we first started with this very basic but actually bad idea where we used a list of sets. We then did quick find, where we stored our connected components as set IDs. We then did quick union, where we store the connected components as parent IDs. And then we had a couple of improvements where we changed the rules for how union is done, and then we added a rule for compressing the tree to make it shorter. Now, we saw there were different flavors of improvements. The first flavor was, actually, there's a few things we did. The first is to realize that we should keep track only of connected components and not the specific connections. That was done at the very beginning of lecture, and that saved us all the headaches of tracking each individual line. After we decided on connected components, we first started with a list of sets, and then we went to an array. And then we changed how we thought about the array, and then we changed how the array was modified, and then we added an additional rule to optimize. So there's a lot of different things we saw, very different ways to optimize how our data structure works. And when you do real world problems, whether it's implementing a basic data structure or trying to solve a real world problem that you care about, you should keep in mind that all of these different flavors or improvements are things you might need to keep in mind. They all really matter. And then to summarize, very finally, our runtimes, we were able to move from having a runtime that is n times m to handle m operations to bounded above by n plus m times the inverse Ackermann function of n, for if you're a theorist. But if you don't want to know exactly what this is, you could just think of it basically as constant, right? So, because it grows so slowly. All right, that's it for today as far as our data structure goes, and I hope you found that set of optimizations really interesting to watch.